Hey, welcome back, Shayla area, to note video number 9 in physics. Today we're going to talk about momentum, and we're also going to talk about what happens when things collide and the kind of changes that take place in the movements when things collide. And we're going to wrap it all up with talking about satellites. So to start, let's broach the topic of momentum. So when you talk about momentum, you have to bring up good old Isaac Newton again. So Isaac Newton's the guy who figured out how to quantify this. And it was a really long time before I felt that I actually really understood what momentum was. And what momentum boils down to is it's a type of kinetic energy. Remember how we learned about temperature? And how temperature is just like the movement of all of the molecules in the atoms and their speeds. And that's a form of kinetic energy, because kinetic energy is the energy of things moving. Well, momentum is also the energy of things moving. It's defined as a quantity of motion. So I guess it doesn't get any more simplistic than it's about kinetic energy. It's about movement. But that doesn't really mean anything. It's really abstract. It's a quantity of motion. Well, what can you put your hand on that? You know, is it a pound? What does that feel like? Essentially, here's what it boils down to: the more momentum an object has, the harder it is to stop. So when something's moving, in order for it to be moving, it has to have kinetic energy. We have this energy of things traveling through space-time. Well, if you're big, if you have a lot of mass to you, if there's a lot of particles that make you up, and you're traveling through space-time, it would take more energy to move lots of particles over that distance than it would to move a small number of particles over that distance. I mean, that just makes sense. And that's what momentum is. Momentum is how much energy there is that's requiring to move all of this matter. So the more energy that there is, the harder it's going to be to stop. And what happens when things collide is that energy starts to flow into other things. You can kind of think of it like conduction. The way that, if you have a hot object and a cold object and you touch them, the way that kinetic energy moves from one to the other and the temperature kind of flows. Well, the same thing happens with momentum. And it's got an equation that's nice and simple. It's just mass times velocity. So to calculate for momentum, you take the mass of the object. Now we do this in kilograms, and it takes the velocity of the object, and we do that in meters per second. But what's interesting about momentum that's different from all the other things that we're talking about is that there's no name for this. There's no unit of momentum. So you can't say it's a Newton as a force. You're not going to be able to say that it's a joule for work, or it's a watt for power. It's literally just a kilogram meter per second. So if you think about that for a second, though, it's a kilogram meter per second. So what's the difference between momentum and force? Well, if momentum is a kilogram meter per second, and we just learned that a Newton is a force, and a Newton is a kilogram meter per second squared, the only difference between momentum and force as newtons is one of these time units down here. Well, that's also the difference between speed and acceleration. So there's a similar kind of relationship there. All right, so let's take a look at some momentum problems, and I think they're actually kind of fun to work out. So problem 1. You're going camping. Well, one of the things you need whenever you go camping is wood. I remember going week-long fishing trips up in Canada, and my job was always to go around in the woods and grab logs, and grab a wedge and a sledge and start splitting up the logs for firewood. Other people will be doing other things, getting ready for camp. So let's say you have two different sledges. One sledge is a 3 kilogram sledge, and another one is a 4 kilogram sledge. So obviously the 4 kilogram sledge is heavier. Well, when you swing one of these big heavy hammers, it's going to hit the wedge with a certain amount of force. See, here I'm using force. It's going to hit the wedge with a certain amount of momentum. It's one of the reasons that it's tough to wrap your head around because you don't know what to call it whenever you're explaining it. So you're going to swing your sledge, and it's going to come down, and it's going to wham. It's going to hit that thing. Sometimes sparks fly off. Sometimes little metal shards fly off. But the momentum that's built up from the sledgehammer is going to go down the wedge. We're going to learn about wedges when we learn about simple machines, and it's going to start to go into the wood. Well, the heavier the sledge, the more momentum it should have, but it has to do with the speed value as well. So let's say we have these two sledges. There's a lighter one that you can swing faster, or a heavier one that you can't swing as fast. Which one is going to do a more effective job of splitting the log? Well, 3 kilograms times 1.5 meters per second versus 4 kilograms times 1 meter per second. Well, it's going to give us 4.5 kilogram meter per second. That's that weird momentum unit versus 4. So to actually do a better job, this would be your better option, the 3 kilogram at 1.5 meter per second. It's a little bit like choosing a bat if you play softball or baseball. The heavy bat, yeah, you can, there's a lot of mass there that you can connect with the ball with, but it's only really effective if you can have it swinging. The velocity is really, it's an important part of this. And then when you start training, do you do strength training to be able to use a bigger bat, or do you do technique to be able to maximize the velocity? Which one are you going to have more growth in? Because it's a one-to-one relationship. So whichever one you're going to grow the most, that's the one you should probably target when you're training. Problem number 2. Well, would you rather step in front of a car going 35 miles an hour or a baseball going 35 miles an hour? And I've had students argue this. They have these reasons why they'd rather get hit with a baseball than with a car, because they're like, baseball hurts. I've seen people break their face and they get big welts and stuff like that. I think that students argue this because, well, what it's like to get hit by a baseball. You can imagine that. Maybe you've been hit by something that's been hard and you're like, man, that hurts. And then you think of a baseball and you're like, that would really hurt. It's impossible to imagine what it would feel like to get hit by a car. You don't have any metrics for that unless you've actually been hit by something that's like as big as a house and coming at you. So it's like I think that's where the argument starts to build from. But there is a lot more momentum behind a car than there is behind a baseball. So from this one, it has to do with mass. The last one, it had to do with speed. Here we have the same exact speed. So the only difference in momentum would have to come from the mass. So would it take more energy to move this many particles of matter through space or this many particles of matter through space? Like we have the law of conservation of energy and we have the law of conservation of mass, it shouldn't surprise you that we have a law of conservation of momentum. And really it makes sense because what did we just say momentum was? Momentum is a form of energy. Right? It's kind of like that temperature situation. So if in case you need reminding on what the law of conservation of energy is, it's the one that says energy cannot be created or destroyed. And then the second part is it can be turned from one form into another. So you can't just make energy without pulling energy away from something else. And you can't get rid of energy without sending that energy into a different form. So if you can't destroy energy, then momentum's the same thing because it's just a form of kinetic energy. So whatever you have, total kinetic energy in the system before any kind of collision, you have to have that same amount of energy after the collision. What is different is where the energy is found, because the energy is going to go from one object into another. It's going to pick up that energy, and then it's going to change its behavior. So let's pretend that we're at the Etna Fair, riding one of those little carnival rides that they have out there. There's 2 cars moving on the tracks, and train A has a mass of 20 kilograms. Maybe just a couple of 4th graders in there. That's not even close. So at 20 kilograms, that's about 50 pounds. And it's moving at 2 meters per second. That's not all that fast. Nice little ride. Train car B, though, is coming up from behind. there's an extra kid in there. So it's now 30 kilograms, and for some reason it's going faster. It's going twice as fast. So it's like barreling down on it at twice the speed. I mean, both of these speeds are less than 10 miles an hour, but, you know, there's definitely going to be a collision. They yell, they point, they scream, they laugh, and the cars collide. Bang! Everybody thinks it's fun. Car B, the one who just rammed into the back of them, has its speed cut in half. It was going 4 meters per second, but then when it collided, it dropped to 2 meters per second. Well, think about this for a second. There's a bunch of energy. There's this energy that's moving, this kinetic energy that's moving all of the particles of that car through space-time. Well, it's going half the speed now. So it's lost a bunch of that energy. That energy had to go somewhere. That energy literally was imparted and like went into the cart that was in front. So the cart in front now has all of that energy, and that's going to make it speed up. The question is, exactly what will its speed be? It's really cool you can figure this out. And it happens instantaneously. That energy just poof, jumps right into the next place. Conduction's kind of slow, you know, where the particles have to run into each other and collide and kind of impart it like one atom at a time. In these kind of problems, it happens all at one time. So, how do we figure this out? Well, you have to figure out the total momentum before the collision. So we have two cars. We have to figure out the momentum of each of them, how much energy is being used to move them through space, and add them together, and you get total. So we have these two cars. One car, 20 kilograms. It's moving at a velocity of 2 meters per second, forward direction. So its momentum is 40 kilogram meters per second. Car B, the bigger car that's moving faster and barreling down on them, 30 times 4, 120 kilogram meters per second squared. The car that's barreling down on it has 3 times the kinetic energy as the one that's about to get hit. There we go. So the total is 160. So after the collision, we have car B. Car B is now, remember, it's still the 30 kilograms. It's not like a kid fell out or anything like that. We have the same amount of mass. But it's not going 4 meters per second anymore. Now it's going 2. So now the momentum of car B is 60. Well, what was it before? It was 100, wasn't it? So it's lost a significant chunk of its momentum. But the final momentum still needs to be 160. So that means the other car has to have how much momentum? Well, if this has 60 and the total is 160, the other car now has to have a full 100 of momentum. So 100 kilogram meters per second. Well, if it has this much energy, if it has 100 kilogram meters per second worth of kinetic energy, and it has a mass of 20 kilograms, we can solve for speed. We can say exactly how fast that car is going to be going. We know its mass, we know its momentum. Well, look at that. Look what happens if you divide the kilograms out. You're left with a speed. And it would work out to be 5 meters per second. So notice, since the car in the back had more mass, when it collided and lost that energy and sent it up, instead of instead of the new car gaining the same amount of speed that the first car lost, it actually gained more because the car was smaller. So it didn't take as much energy to make it move faster. So here's the rub with the collision problems and trying to use them in real life. It's nearly impossible to use these to actually predict what's going to happen and predict the future, like I said before, unless you can control a whole lot of variables. And like if you were a stuntman, it's unbelievable how many variables they control when they conduct some of those stunts for movies and things like that, because they're so dangerous. But it's just they know exactly what's going to happen with the physics as long as they did all the math right. But in a collision, you don't always have one thing running into the other and then moving slower and giving us some of that energy. Sometimes you'll have one thing running into another and stopping. Sometimes you'll have one thing running into another, and they'll both, if you were going to use some geometry skills, which is what you'll do in the high school, like two pull balls running into each other and then both careening off at different angles. Well, you can predict all of that. But sometimes you have things running into each other and then they stick together. Sometimes you have things running into each other and like jumping over each other. And these are all the things that you can't quite predict the future on, but we can set up situations and say, if we know what one of the balls does, we can definitely say what the other one would do. All right, so here's the second one. So in scenario number 2, we have a 20 kilogram car again. Now it's sitting still. In this scenario, it's not moving. It's stalled out. The kids are just sitting in there. And the car B, same mass, coming up behind it at a speed of 5 meters per second. The collision causes car B to come to a stop. You've probably seen this on a pool table if you've ever shot pool. If you hit the ball just right, the cue ball will move and hit the object ball, and the object ball will take off, and the cue ball will sit right where that ball was. It's kind of a neat thing to see happen. Well, our total momentum, these ones are nice and easy because, look, if your speed is 0, your momentum has to be 0 because it's a multiplication sign. So in the beginning, the only momentum in the system is coming from the train in the back that's coming at 100 kilogram meters per second worth of energy. So our total beginning is 100. Our total in the end also has to be 100. Well, in the end, the car B is stopped, so it's 0. So that means every bit of momentum was transferred into the other ball. Well, the other ball is exactly the same mass, so it's going to be 5 meters per second. That's kind of the math behind the identity property. And whenever you learn about that and you're like, hey, 1 equals 1, and you're like, thanks, I'm glad you taught me something. I didn't know 1 equaled 1. But it's a really important concept in math to understand, the whole equal sign, the power of the equal sign. Well, in this case, if you have an object, 2 objects of the same mass, and it gives all of its momentum to the other one, well, it's going to be going the same speed. You haven't lost any energy. Keep in mind, in the real world, you have friction in all these collisions. We pretend like friction doesn't exist at this point. All right, so quick check. Here is one. Let's see if you can figure this out. This is one where we have the 2 cars going. 40 kilogram train car sitting on the track, so it's sitting still. Remember what we did with that. If it's got a velocity of 0, then it's got a momentum of 0. Car B is 30 kilograms, moving at 7 meters per second. It's chugging along. It's fairly quick, really fast for one of these rides. And then they collide, but the little couplers click together. So now it's like a real train where they're linked together. What would the speed be? How fast would the 2 cars combined be going after the one in the back slammed into it? You can figure that out. Do it just like we did the other ones. Just remember, on the finish side now, you just have one object, and it's car A and B together. Satellites. Satellites work because of centripetal force. Centripetal force literally means center seeking. It's force that an object experiences that makes it want to move towards a center of an arcing path. It's a really interesting thing to discuss, and it has to do with inertia, and it has to do with lots of things. So if I'm moving this way, the red probably wasn't the best color. Let me change colors here. But instead, I turn this way. If you were in a car and did this, what direction would you move? So let's say you're riding in the car, and you're down here. And the car's going, and the car's originally going along the red line and then makes that left-hand turn. Well, you would fly towards the outside of the car, right? Like that's the way that you would feel like you were going. There is a lot of complicated stuff that happens in here. If we were to map out the actual vectors with all the arrows like I showed you on the inclined plane that one time, there's a lot of stuff going on. I'm not going to explain it here. But in the end, the forces that end up winning out are the ones that are center seeking. So this feeling is called centripetal force. Maybe I'll design a homework assignment around it. We can measure some of these lines and figure out what some of these forces are. We'll see. So just know as a definition that centripetal force is center-seeking, and it's what an object experiences when you go around curves, or like if you were tied to a string to a center post and swing around. It's like the classic example of putting water in a bucket and swinging it over your head and the water doesn't fall out. That's all because of centripetal force. A lot of people incorrectly put an F in here when they say it. It's not centripetal, it's centripetal. It's a very commonly mispronounced word. All right, satellites. A satellite is anything that orbits something else. So when you think of a satellite, you probably think of the man-made things that we launch up in the sky with rockets, and we use them to talk with our cell phones, or satellite phones, or they beam TV down to our houses, or governments have communication satellites up there, or spy satellites with cameras on them, or satellites that are telescopes and we look out into space with them, like the Hubble. The International Space Station would be a type of satellite. Satellite is anything that orbits another. What people sometimes don't think about, though, is that satellites don't have to be artificial. Satellites are a natural thing. There's lots of things in the universe that orbit other things, and all of those things would be considered a satellite. For example, the planets. We orbit the sun, so we are a satellite of the sun. And then everything that would orbit us would be a satellite of the sun, like the moon. Remember in the last note video when I talked about Newton, and he figured out that the orbits aren't circles and they're actually this ellipse shape? Here's a good picture of that. The Earth here is found at one loci of the ellipse. The other loci would be up in here, and if you had a string and drew around in a circle, that's the shape that you would get. You would get this elliptical shape. So satellites can be man-made, but they can be totally natural as well. Here's what's neat. I find this very interesting. So, in space, let's go to whiteboard here. In space, you have, come on, go away. We'll call this the Earth. Nice. And we have a satellite. Well, let's freeze time. Freeze time, all motion has stopped. Now we are going to let time go again. Hit play, we're going to keep going. But all of that momentum is lost. All right, there's none of that kinetic energy anymore. Well, what's going to happen? Well, the satellite is going to fall straight down and crash into the planet. Right? That's what it wants to do. Remember, with all of our projectile equations, vertical motion, vertical velocity, and horizontal velocity are completely separate things. So, if we would stop all momentum and then start it again, and what would happen is this thing would fall down and crash to the Earth, that's what it wants to do all the time. That's the vertical motion. The vertical motion is like happening because of gravity, and then if you want to get really crazy on it, is that when this thing has moved over in this position, remember where vertical motion is. Yeah, vertical motion is now this direction. Because what's vertical is always the straight line between the center of the planet and you. So your direction of vertical would change if you were at a different spot on the planet. People along the equator think of vertical as a totally different angle than you do. People on the other side of the planet think of vertical in the same way that you do. It's just upside down. So anyway, we have these satellites that have this vertical component where they're falling. Well, gravity is pulling everything out in space within its reach towards the planet. So why don't all these things come crashing down to the planet? Well, I mean, the planet does get rained on by space debris all the time. Like millions of pounds of space debris burn up in the atmosphere. Some of it actually reaches the planet, but we keep adding mass to our ecosystem, to our whole global ecosystem from space, and have been ever since the planet's been here. But these satellites aren't sitting still, so that's why they don't come crashing down into the planet. They're going fast. Remember, the speeds that things are traveling, when you're talking about like space like this, remember the planet is moving 32,000 miles an hour around the sun. Like, that's how fast we're orbiting the sun. So everything around us is also moving really fast. We start to have this reference point situation going on. So these things are falling towards the planet, but they're also moving forward. So as they fall, they form this arc. And remember, if you want to like turn your head, it's now falling this direction, but it's still moving forward. So we're going to change colors. So it's falling and it's going to make an arc. And you know, when it gets over here, it's going to want to fall towards the center of the planet, but it's also moving forward. Remember, this is down now. This spot right here is now down if our satellite is here, and it's going to keep falling forward. So it's going to look like a circle, but if you can imagine what's happening, let me wipe all this out. Imagine if this was the Earth. We'll zoom in a little bit. Here we got the Earth, and we got some ocean going on here. And we'll just call that a polar cap. And here we have a satellite. Try like a TIE fighter bow tie kind of thing. All right, it's falling, but it's also moving forward. And what happens is it misses the planet. It's moving forward at such a speed that by the time it reaches this distance, remember how you would calculate time? How much time would it be in the air? By the time that it would reach the surface of the Earth, it has moved forward so much that it misses the planet. And the situation is just constantly updating. You know, it's just constantly falling and constantly missing the planet. It's like the worst aim ever. And if you set this speed perfectly so that it always misses the planet, it will just continuously go around the planet. And we call these things stable orbits. If you do the math on the size of the sun and how much mass is in the sun and its gravitational pull, and you do the math with different speeds, there are specific places in the solar system that form these stable orbits with these really nice speeds. And that's where the planets are found. That's actually how we discovered several of the planets. We didn't discover the planets because we were watching the sky and like saw something and thought, well, that's interesting. We were watching the sky and we were doing math and we were figuring out how big these objects were. And then some people were like, you know what? With the size of these objects, there should be something right here. This is a stable orbit. There should be something along this path. So if we look right here long enough, and lo and behold, hey, look, there's Uranus. Like, that's how we discovered some of those planets, through math and through our understanding of these kind of kinetic energies and where things would have to be if they were going these certain speeds. And the gravitational pulls on other things. That's what like astrophysicists do. So anyway, I always thought that was really neat that satellites are falling and just completely missing the planet. So I can say I have better aim than a satellite, but barely. Fun fact, goes along with the gravity pitch gizmo that you're working on right now. If you stood on the top of a high mountain, like Mount Everest, threw a ball horizontally, because remember we're not doing anything with angles yet, and you could throw a ball 17,700 miles an hour, that ball would go around the planet and smack you in the back of the head. Wouldn't that be fun? And on that note, booby trap number 9. This is the last note video before the second quiz in physics. So, good luck.